I'm just going to do a few extra examples in this video. So this is good to watch to help you practice for the midterm coming up. So let's do another logical equivalence example. So we want to use logical equivalences to show that P and Q implies R or S is logically equivalent to P and Q and not R implies S. So before you watch the rest of the video, pause the video, try it yourself. See if you can make the left side here look like the right side. Okay, now that we're back, let's look at this. So I'll tell you how I'm thinking about this, and hopefully this gives you some sort of idea about a good way of approaching it. I see this implication, I'm thinking, well, maybe it's a good idea to use the conditional simplification to make this into not this or this. So not the if part or the then part. If I do that, I'm thinking that I'm going to get, well, this is going to switch to not this, and then by De Morgan's law, I'm going to switch it to a bunch of ors, and then this is going to be just R or S, so a bunch of ors. So in some sense, that's really good, because the only logical equivalence I'll have is a bunch of ors, and then I can rearrange those ors in whatever way I think is appropriate. And looking at this, P and Q and not R, there's a very good chance I can use De Morgan's law again in the other direction to make this happen. So that's my goal here. And then once I get kind of something along the lines of not P and Q and not R or S, then I can use the conditional simplification in the other direction. That's how I'm thinking about this. Let's give it a go. So we'll start with the left-hand side. P and Q implies R or S. That's equivalent to, let's use conditional simplification, so it's the negation of the if part, P and Q, or the then part, R or S. That's by conditional simplification. I believe that's 12. Now let's use De Morgan's law here. So using De Morgan's law, I have the negation of something with an and, so everything gets negated, even the logical connective, so it's not P or not Q or R or S, and that's using De Morgan's laws. And then, well, what do we want? We want something along the lines of not this or S. So what I'd like to do is to group all three of these together and apply De Morgan's law. Now, we don't have a logical equivalence for De Morgan's law with more than two things here with one connective. It ends up being the same. So I'm going to do it the long way, just to make sure we're doing things appropriately. So I'm going to group these two together. So this becomes not P or not Q or R or S, and that's by 3. Great. Now I'm going to use De Morgan's law to make the square bracket become the negation of P and Q or R or S, and that is by De Morgan's law. Okay. And now I'm going to group things like this. So I'm going to use De Morgan's law once again with these two objects, the negation of P and Q and R. So they're the two objects where I'm going to use De Morgan's law again for. So this becomes the negation of, and I'll use big square brackets again, the negation of, well, here I have the negation of P and Q, so it's not P and Q. Remember, I'm treating this guy as one object, so the negation of that is just P and Q. Switch the logical connective, or becomes an and. This becomes the negation of R or S. And that is by De Morgan's law yet again. And we used the negation of a negation is the original thing. So that's that step. And then, well, looking at this, we're almost done. We have P and Q and not R. And here we have P and Q and not R. We have or S. So all we're going to do is we're going to use our conditional simplification to make this into a conditional. So this is the same thing as P, I wrote RP, and Q and not R implies S. And that's by the conditional simplification. So we have not the if part or the then part. So if, then. That's how that works. And in some sense, we're using the idea of associativity here as well to kind of drop these brackets, saying they don't matter. So just to be extra careful, I'll put that we're using associativity there. For the midterm, don't worry too much about labeling the steps here. As long as you're writing down correct things, you're good to go. All right, let's look at this one. This is just a nice direct proof problem. So we want to assume that if this expression here, x squared minus 7x plus 12 equals 0, and x is a real number, just to say the domain of where x lives, then this expression, x minus 7 halves all squared equals a quarter. So remember, for direct proofs, you want to assume the if part is true, show that the then part must be true. Now, when you assume the if part is true, maybe you can use that to deduce something about what x needs to be. And if you think about it, we have a quadratic here. So at most, there are two x's that make this 0. That might help you out. So pause the video, give that a go. Okay, now that you're back, let's prove this. So proof, switch to my black pen here. Let's assume that x squared minus 7x plus 12 equals 0. And does this factor? We could use the quadratic equation as well, or quadratic formula, sorry. But looking at this, can I come up with two numbers that multiply to 12 and add to minus 7? Well, minus 4 and minus 3 do it. So I can rewrite this as x minus 4 times x minus 3. That equals 0. And you can check yourselves that if I multiply this back, I'm going to get x squared minus 7x plus 12. So this tells me that either x equals 4 or x equals 3. There's two different cases here. And remember, we have two numbers here, x minus 4 and x minus 3, that multiply to give you 0, which means one of these must be 0. So x is 4 or x is 3. So we want to show that this expression, x minus 7 halves squared, equals a quarter. So in some sense, our if part is just kind of a hidden version of if x equals 4 or x equals 3, then this expression equals a quarter. So let's go ahead and do this. We have two cases, so it might be easiest just to fill it in and check for each case. So case 1, x is 4. Then x minus 7/2 squared is, well, x is 4, so it's 4 minus 7/2 squared. 4 is 8/2. 8/2 minus 7/2 is 1/2 squared, which is a quarter. So if x is 4, this is true. Case 2, let me do this in black. Case 2 is x is 3. So let's check. Then x minus 7/2 squared equals 3 minus 7/2 squared. 3 is 6/2, so 6/2 minus 7/2 is negative 1/2 squared. And negative 1/2 squared is also a quarter. So we're good. So in either case, the result is true. Maybe write a little note at the end. Thus, the result is true. In both cases. And we're done. So there's an example of a nice if-then proof. Remember, assume that the if part is true, and you might be able to reason something about that if part. And in this case, we could reason that x must have been 4 or 3, or must be 4 or 3. Using that knowledge, we can show that the then part must be true for either case. All right, let's do this example here. So this one is an if and only if statement. So we are going to have to do two directions. This is two different proofs. We want to prove one result and its converse. So again, let's talk about the different directions. The first direction, we're going to prove that if n plus 5 is even, then 3n minus 1 is even. And the second direction, we're going to prove if 3n minus 1 is even, then n plus 5 is even. And remember, for each of these sub-proofs, if you will, maybe it makes sense to prove the contrapositive for one of them. So pause this, give this a go, see how it works for you. Okay, now that we're back, let's prove this. Let's do the forward direction first. So that's, I'll write it out just to make sure we understand what it is. If n plus 5 is even, then 3n minus 1 is even. So if this is our P and this is our Q, this result here is P if and only if Q. We are proving P implies Q. Okay. So looking at this, I'm going to try doing a direct proof for this, and the reason that I note that is I think n plus 5 is a little bit simpler than 3n minus 1. To get some information about n itself, I wouldn't have to divide by anything. So that makes it seem a little bit simpler to me. So I'm going to try just a direct proof and see if I can do this. So let's go ahead. I'll just do a direct proof here. So let's assume that n plus 5 is even. Well, if n plus 5 is even, what does that tell me? That tells me that n plus 5 equals 2 times k for some integer k. And if I can get some information about n, I might be able to plug it in to 3n minus 1 and then show that that must be even. Okay, so then, thus, n is, we'll subtract 5 from both sides, 2k minus 5. So I have some information about n. So let's consider the then part, 3n minus 1. We want to show that this is even, so it equals 2 times some integer. That's our goal here. So this equals 3 times n, and we said n was 2k minus 5 minus 1. All right, let's expand this out, collect our like terms, see what we have. So we get 3 times 2k is 6k minus 15 minus 1, which is 6k minus 16. And I'm in luck. There's a factor of 2 in both terms. Might as well just cancel them out, or factor it out, sorry. So this becomes 2 times 3k minus 8. And since 3k minus 8 is an integer, we're just adding, or sorry, I should say subtracting and multiplying integers. That gives us an integer. So since that is an integer, we have that 3n minus 1 is even. So we've done the first direction. Let's do the second direction. So again, I'll write out the second direction. So we're going to prove if q, then p. So if 3n minus 1 is even, then n plus 5 is even. That's the other direction. Okay, looking at this again, I would rather solve for n in this part than in this part. So maybe it'll be easier to do the contrapositive in this case, because it'll be easier to get some information about that fundamental piece n. So I'm going to try the contrapositive and see that that works. So we're going to assume the then part is false. We're going to show that the if part is false. So by contraposition, let's assume n plus 5 is not even. And since we're in the integers, it means that n plus 5 is indeed odd. Thus, n plus 5 equals 2k plus 1 for some integer k. Excellent. Okay. So again, we can just solve for n. That might help us out here. So n, we're going to subtract 5 from both sides, and we get 2k minus 4. So we have some information about n, and we can plug it in to 3n minus 1, or I should say this 3n minus 1. We want to show that this is false, so that 3n minus 1 is not even, that it's odd. So we want to show the if part is false. So to show, I'll write this down because we're doing the contrapositive. 3n minus 1 is odd. So 3n minus 1 is 2 times some integer plus 1. Okay, so let's go ahead and do this. Let's consider 3n minus 1. This is 3 times 2k minus 4 minus 1. Okay, so let's expand this out. We get 6k minus 12 minus 1, which is 6k minus 13. Now, I would like a plus 1 here, because that's the form that we like to write odd numbers in. So maybe what I'll do is I will add 1 and subtract 1. Or you can think of it as just like taking out a plus 1, so this would be minus 14. However you want to do that. But this becomes 6k minus 14 plus 1. So that minus 14 is the minus 13 minus 1, and then here is our plus 1. So again, we have these two terms with a factor of 2. Take it out. 2 times 3k minus 7 plus 1. And finally, we just say since we have 3k minus 7 being an integer, we know that 3n minus 1 is odd. And we're done. We proved what we wanted to. We did both directions. Okay. So, in this question, we're asked to disprove a statement. And the statement is, if we have two non-empty sets, then the union of the power sets of each of them equals the power set of the union. So we want to disprove this. So we need a counterexample. We need something where the if part is true and the then part is false, since we have a conditional statement here. So we want to find two non-empty sets where this is indeed the case. Where if we take the power set of A and the power set of B, take the union, that it doesn't equal the power set of the union. So pause the video now and see if you can work this out yourself. Think about what you would need to show and see if you can find a counterexample. So let me tell you how I'm thinking about this. Because a lot of times to develop a counterexample, you have to kind of think about what each object means and what's happening. So remember, the power set is the set of all subsets. So we need, here's the set of all subsets of A. Here's the set of all subsets of B. So I'm thinking, if there's an element in A that's not in B, and an element in B that's not in A, well, I'm not going to see a subset of A that includes that element not in B, and a subset of B of that element that's not in A. But there will be a subset that contains both elements in the union. So let me give you my counterexample. It's probably easier to explain when I write it down. So let's let A be the set 1, and let's let B be the set 2. Okay? Well then, the power set of A, well, that's easy. There's just the empty set and the set containing 1. So itself, they're the only two elements of the power set because they're the only two subsets of A. And the power set of B is the empty set and itself. And that is it. Now let's look at, now we need to take the union of these guys. So the power set of A union the power set of B. Well, what's in this? Well, we have the empty set, we have the set containing 1, and we have the set containing 2. And the most important thing here, in some sense, well, we know there's 3 elements. So the size, the cardinality of this set is 3. You have the empty set that was in both. You have the set containing 1, which was in the power set of A, and the set containing 2, which was in the power set of B. So there's 3 elements. Okay, so note, also, maybe we'll say also, we know that A union B is the set 1, 2. So we know how to take the union of 2 sets. A is just 1, B is 2. So the union is 1, 2. That's pretty easy. Now you could list all of the elements of the power set of A union B and find that there's one in there that's not in the power set of A union the power set of B. But I know that since the size of the power set of some set, let's say S, is 2 to the S, I know that the size of S, the cardinality of S. So, and we know that the cardinality of A union B is 2. There's 2 elements in it, 1 and 2. Well, I know that the size, the cardinality of the power set of A union B is 2 to the size, the cardinality of A union B, which is 2, and 2 squared is 4. And 4 doesn't equal 3. Since these sets here, the power set of A union the power set of B, since that set and the power set of A union B, since they have differing amounts of elements, they can't be the same set. Since the cardinality of the left-hand side doesn't equal the cardinality of the right-hand side, these sets can't be equal. Or alternatively, you could just note that the set 1, 2 is going to be in the power set of A union B, and it's not in the power set of A union the power set of B. That would be enough to show it as well. But remember, what you want to do is you want to find something that proves that this is a false statement. Since it's an if-then statement, it's false exactly when the if part is true. The then part is false. All right. In a similar vein, rather than showing that these sets aren't equal, it turns out that the power set of A union the power set of B is a subset of the power set of A union B. So remember, to show that one set is a subset of another, take an element from the left-hand set here, show that it's in the right-hand set. That's how to show something is a subset. So pause the video now. Your first line should be, let's call it X. Remember, elements of these are going to be subsets of A or subsets of B, so we'll call it X is an element of the union of the power set of A and the power set of B. So what does that mean? So go from there. So pause the video now and try it yourself. All right, now that you're back, well, remember that elements of power sets are subsets of the set the power set was taken of. So we know that if X is an element of the power set of A, so X is an element of the power set of A, or X is an element of the power set of B. Which means, well, if it's an element of the power set, it means that it's a subset of the original set. Or X is a subset of B. So you can see that there's nothing really different about sets A and B in our results. So this is a time we can use without loss of generality. So without loss of generality, less X be a subset of A. The work when X is a subset of B will be the exact same because there's nothing that differentiates those sets in our problem. Well, if X is a subset of A, what does that mean? Thus, for every little x in big X, we know that X is also an element of A. Thus, X is an element of A union any set that you like. And so the set that we can pick is B. So since X is an element of A union B, so we started with an element of X, and we showed that any element of X is also in A union B, well, that means, and thus, X is a subset of A union B. So, if X is a subset of A union B, well, that means then it's an element of the power set of A union B. And remember, that's what we wanted to show. Maybe we could have wrote that up here just to make sure we understand what's going on. We assumed X was an element of the power set of A union the power set of B. And we wanted to show that X was an element of the power set of A union B. That's what we needed to show. So we just did that, so we're done. Our result is proved. Maybe we can write a little sentence, actually, just to make sure people understand that we're done. Thus, the power set of A union the power set of B is a subset of the power set of A union B. So these two sets that we learned in the last example, they're not equal, but this left-hand side is indeed a subset of the right-hand side. And just to reiterate, remember, for any of these subset things, you assume an element is in the left-hand side, you show it must be in the right-hand side.